Alright, so having done some work with Gauss's theorem now and some examples, I want to revisit the conclusion of Gauss's theorem and just look at this. Well, so first thing that we notice is that, well, okay, to state the obvious, this is a vector surface integral, okay? And we also, in the examples, we're using the term of flux for this, okay? And to, again, state the equivalent obvious here, this is a triple integral, right? And so the triple integral, we can think of this as, in quotes, adding up infinitesimal net flow in D, right? That's what the three oh gosh, I can't even remember the name right now. The three dx, dy, dv, or dx, dy, dz rather. That's what those mean. And I can't remember the life of those mean. What there's a term for that, and I can't remember it right now. But that's what those are indicating. All right. And when we think about flux, at least conceptually, that is the idea of total flow across the boundary. Okay. Well, okay, and then we want to recall that when we use the symbol, the del operator dotted with F, that is, I let it slip in the last video, but that's the divergence, right? And that measures infinitesimal net flow. And when we first discussed divergence, we were thinking of it like this. We were looking at a region and how the vector field was flowing through an object that we place in it. Well, this kind of sounds familiar, right? So if we jump back to week 10, and I happen to have those handy, it's right here. So we were talking about, in week 10, the divergence theorem, and we were just focusing on it in the plane, so we were focusing it in 2 dimensions. And so, right, we saw all this, and we said, okay, well, we have a closed vector line integral, and then we had to do a dot product here, and then that's equal to, and then this was the divergence, right? And then, great, and we called that the flux, okay, so, and then we said total flow across the boundary was equal to total net flow. This is like all the same as what we're doing, we're just going up in dimension, so this is now the full divergence theorem. Okay, so when we talk about Gauss's theorem in general, we sometimes we also equate this to the divergence theorem. Okay, theorem. And if you want to specify that it's in space, hey, great, go for it. Okay, but that's kind of the punchline here. All right, so just to equate the language, knowing that Gauss originally developed the theorem. That's really the reason why we call it Gauss's theorem. All right, so next video we'll talk about volume a little bit.